Okay, so this is going to be a response to Rusty the Robot Bear. Basically, he left a comment of a thought experiment on I Could Science That's channel, and I'd just like to respond to it, but I feel like the best way to do it is with visuals maybe, and explaining. So basically, he says take a box chock full of vacuum, accelerate it up, down, left, right, no gradient, whatever you do, because there's nothing in the box to form a gradient. Okay, I can essentially agree with that. I mean, technically you can't get perfect vacuum, but I can essentially agree with that. Put an inflated balloon in the box, doesn't matter what's in it, because any gas will be denser than the vacuum around it, but make it tough enough not to burst as the balloon expands because of the vacuum around it. Okay, let's say we put helium in it. Okay, 3. Sit the box on the ground. The balloon will sit at the bottom of the box, even though there's no gradient in the box. Question, why is it at the bottom? As you said above, everything is denser than a vacuum. So, if it's denser than a vacuum, according to relative density, it will go down. So, okay. Lift the box off the ground a few metres and then accelerate it to the right at, say, 10g. The balloon shifts to the left, up against the left-hand wall. Question, why does it do that when there's no gradient in the box? So basically he's trying to say that, you know, you accelerate in one direction and then the balloon will go in the opposite direction in a vacuum. See, I don't really agree with that at all. So this is where our thought experiment breaks down, and we'd actually have to do the experiment to find out, because the way I think of it is obviously different to the way he thinks of it. Okay, so basically he says, you know, accelerate in one direction and the helium balloon will go in another direction in a vacuum. Okay, so it will go in the opposite direction to the acceleration in a vacuum. But if we go back to the car experiment with the air in, you know, I'm sure we've all seen it, I think it was Smarter Every Day. Obviously when he has the helium balloon in that, the helium balloon goes in the direction of acceleration. And this is what I'm trying to say, that acceleration is not the cause of the movement. Because in a vacuum, he thinks that the helium balloon will go in the opposite direction to acceleration. Yet in a car, so if we had the same box, for instance, and then we put air in it, now the helium balloon will go in the direction of acceleration, opposite to what it would have done, or what he thinks it would do in a vacuum. So therefore, the only thing that changed is the medium, and yet the direction changed. So therefore, the medium obviously was the cause of the direction change, because that's the only thing that changed, right? Like, you can have the acceleration in the same direction with a vacuum, and he reckons the balloon will go the opposite direction to acceleration. If you then fill that vacuum with air, the helium balloon, as we've seen with the car, will go in the direction of acceleration. So therefore, that's two different results, with acceleration being exactly the same, and the only thing changing is the medium. So obviously the medium does cause objects to move in a certain direction, because, you know, obviously they don't work, do they? Like, you know, if you keep the acceleration and then you say in a vacuum it goes in the opposite direction, but then you add the medium and then you say the helium balloon now goes in the direction of acceleration, the acceleration obviously wasn't the cause, right? I mean, you kept the acceleration and you didn't get the same effect. So clearly it was the medium that was the cause. So yeah. And then basically, if we had, say, an object in a vacuum, so we'll just go with a person. We'll go with an astronaut. Why not? In a vacuum of space, there's no masses around it, there's no gravity, there's no forces acting on it, okay? Let's give him a helmet and a spacesuit, yeah? Or it can be a bowling pin, but you know, it looks like a bowling pin. Okay, so basically this object is stationary. It's not moving, there's no forces acting on it, okay? And then we put it in a container. Okay, so we put it in a container. Then we accelerate this container to the left. Is accelerating this container to the left going to have any effect whatsoever on him or this object? No, it's not. All that's going to happen is this container is going to move over here and then move over here, because obviously it's accelerating this way, which obviously means that this one needs to move forward. So obviously this will come forward like this, and then it appears like he's gone backwards, but really he hasn't. The container's just moving, and the container hasn't had any effect whatsoever on anything in this container. So then if we, sorry about that. So then if we have, you know, a container again, and then we have air inside, and we just say this was all the same density air, okay? So let's just say it was all the same density, okay? And then you accelerate this container to the left. Is that going to have any effect on any of this air inside? No, it's not going to have any effect. It's not going to directly impact or affect or, you know, have any influence at all on any of this air. All that's going to happen is that the container will be accelerating faster than what the air particles are moving this direction. So obviously they're moving all directions, but the only direction that really matters is the direction of acceleration. So if you say the box is accelerating this way, and these are accelerating faster, the box is accelerating faster than the air molecules, then obviously the box is going to move over, and these are not going to be fast enough to move over here. So the box, so the box is moving faster to the left, okay? And then essentially, again, the box is just going to come over. Because these molecules are not moving fast enough to, you know, get over here, you end up with less dense over here and more dense over here. So the acceleration didn't really cause the gradient. It was the container. So basically, if we say that, you know, we had a floor and we had, again, the same density air above this floor, and then we accelerate this floor to the left, that's not going to affect anything here. You know, like, you can accelerate this to the left and nothing's going to change to the molecules here, because acceleration does not cause a change. So if we accelerate to the left, that's not going to affect anything here at all. The density is not going to change. You're not going to get, you know, less dense over here and more dense over here because the container's moving faster than what the things inside are moving. But instead you'll get like nothing happening. So the floor will accelerate and this will stay the same, which is why I say you need a container to build up the pressure differential, because then with a container you can build up the pressure differential if the container is accelerating faster than what these are moving, and then you can get the pressure differential. But you cannot get the pressure differential without a container. So if we just, you know, had this like this and it wasn't in a container, as Rumpus says, gas likes to run about in that, but yeah, you're not going to get that pressure differential like that, are you? You know what I mean? It's just not going to happen. So yeah, that's my point. And then obviously he says things accelerate in the opposite direction to the acceleration. So I came across this video.
Here we go. And start.
So you can see
I'm just
that these things are stationary, and then when the treadmill starts accelerating, when the floor starts accelerating, these don't move backwards. So let's put it in the best quality we can. Okay, and
I'm just gonna start it. Here we go. And start.
and you can see that they didn't move backwards at all.
Alright, you ready?
So even if we slow it down,
I'm just gonna push. I'm just gonna start it. Here we go. And start.
okay, so yeah, basically you can see that by accelerating the treadmill floor towards the man, the objects on it did not go backwards. They did not go in the opposite direction, even though the floor started accelerating.
Alright, you
So
ready?
they're all stationary.
I'm just gonna push. I'm just gonna start it. Here we go. And start.
Okay, he's accelerated in one direction. Obviously the treadmill's gone towards him. Those objects on the treadmill did not go backwards.
Alright, you ready?
Not even slightly.
I'm just gonna push. I'm just gonna start it. Here we go. And start.
So yeah, acceleration does not cause an acceleration in the opposite direction. That's not what happens. So yeah, hopefully you can see that, and hopefully you can see why I'm trying to say that it's not acceleration that's the cause. And without a gradient, you will not, without a container, you will not get a gradient, because the container is the reason for the gradient, because the container is moving faster than the things inside of it, so they can't catch up, so then you end up with a gradient. That's what I'm trying to say. That's what I'm trying to convey. I hope you can see that. So yeah, take care and stay safe.